Okay, so how you guys doing today? Yeah, perfect. So we actually cover chapter 1 and 2 and 3. So from today, I'm going to show you a practical problem so we can do it together. So you have a really good idea what type of exam problems you'll see on the actual exam. Okay?
When's the shows?
So we're in Wednesday part, so it will be 2 weeks from today. So that will be 17th of February. So it's just 2 weeks from today. Okay? So we still have quite a time. Okay. So, and if you're in Friday's part, it will be 19th. All right. So let's do one chemical equation once more, and then maybe you can have a question like this one. Okay? So you have this one goes in. This is what we did last time too, but try to balance this one. So basically, the numbers that we're filling in right now is what we call coefficient numbers that we've been talking about for weeks. And then this is the chemical equation of the organic compound combustion reaction. So for example, if I give you some numbers, like this is now 32 grams, okay? You have 32 grams of this one, and you have 100 grams of this one, okay? So, or let's make it 150 actually. And you can find out how many grams of these two products we produced, okay? So in here, what you really need to do is try to find out the molecular weight of these two. The reason why we're doing this is we're using the ratio. We call this molar ratio. We're going to compare these two numbers and see how many of these two will be actually going to be used for the reaction. Okay, so you're going to divide this one by it's a molecular weight. Okay, this is 1 carbon, 4 hydrogen. Okay, so it'll be in total 16 grams per mole. Okay. So if you do actual mass, which is 32 grams that you have for the methane, divided by molecular weight will give you 2 moles. Because you have unit mass is cancelled over here, 2 moles. And same thing for this one, this O2, so it'll be 16 times 2, that'll be 32 grams per mole. So if you try to divide this one by 32, okay, so this will be about 4.9 or 8 something type of moles over here. Okay. So if you have this moles numbers of these two reactants here, for methane and your oxygen gas molecule are in moles now. So if you think about one goes in to interact with the 2 oxygen molecule, meaning if you have 2 moles of methane, you need to have 4 moles of the oxygen. Because if you have 2 moles, then you're comparing this one to here, that means 1 to 2 ratio. So it's actually 2 over 1, that gives 4 moles of oxygen is required for 2 moles of methane. Okay? So by just doing this molar ratio simple calculation, you know which one will be your limiting reagent. So tell me which one is the limiting between these two. Is it methane or oxygen, do you think? So you have 4 moles of oxygen is required, but you have more than what you need. So
I think it's going to be your limiting factor.
perfect. This is your limiting. This is our limiting range. So once you choose this one over here, you can stick to this number, moles number of our limiting reactants, to estimate how many moles of these two will be made. Okay? So you can have 2 moles. So 1 makes 1 carbon dioxide, 1 methane makes 2 water. So that makes 2 moles. It also makes 2 moles over here. But this one will be 2 over 1. So this is 2 from 1 methane. So 2 over 1. That makes 4 moles of water. Okay. And then you got the moles of the carbon dioxide and water. You just simply need to multiply that by molecular weight, which is 44 gram per mole. It's 88 grams. This is the 1 to 2, right? So there'll be 4 moles of the water. So it'll be 72 grams. Okay. So this is what we did last lecture. This is a quick review what we did, and this is something you may also see on the exam too. See, but once again, this is one of the really difficult, like the most difficult topic in Jenkin 1. Okay, so let's try to do one more, and I'll move on to the next one. Okay. Okay, how about we do this one? Okay, and I'll give you 24 grams of graphite, okay, here, and then I'll give you, let's try to think, maybe 64 grams. Okay. Can you guys guess how many grams of product will be there? I'll give you about 3 minutes. So you're using different chemical reactions here, but it will be much easier than other, because it's very one simple combination reaction we learned before. Now we're going to use it for stoichiometry to measure how many grams of product will be actually produced if you have this many grams of these two. Okay, it's pretty much the same. Actual mass divided by atomic mass or molecular weight. You see at the moles of each reactants, and look at the coefficient number in the reaction equations to compare how many of reactants will make how many of products, and it will tell you some answer for your final mass of the products. Okay, so 2 or 3 minutes, you can try. And this is what we do every day in chemistry lab. It's a very good fundamental skill we need to know as a chemist. So stoichiometry is just everything. Okay, so maybe 1 more minute, because it's pretty straightforward, simple question. All right, so the how many moles of carbon do I have right now? Perfect, thank you. Okay, how about this one? Perfect. And are you happy with the 111? Right? Yeah. Okay, perfect. It's 1 carbon, 2 oxygen, 1 carbon, 2 oxygen. So there will be no limiting or abundant, they're all used up, right? So meaning you're going to have 2 moles of carbon dioxide. Once again, carbon dioxide is 44 grams per mole. Okay, so the 2 moles times 44 grams per mole will give you 88 grams of products. So pretty easy, right? It's not that bad at all. Only thing you really have to know is how many moles of each reactants will interact based on how many coefficient number were assigned to this reactants. And then you can estimate, oh, this might be the moles of the product they'll actually form. So you can multiply that number by molecular weight. That is your final mass of the product. from your actual ranges. So okay. There's one more. Okay. So that makes sense, right? Can I move on? Let's try to move on. So on your exam, this is some of the type of problem you may see. It's quite, I think, relatively speaking, easier than the conversion ratio. Anyway, so let's try to do one more about the empirical formula. So this is also what we did before. Empirical formula simply is like this one. If you have C2H6, okay, C2H6, you just need to find the common multiple numbers to divide those two numbers. So this is actually telling you how many carbons and hydrogens you have in those compounds. So we call this molecular compound. Molecular formula, I'm sorry. Molecular formula. So molecular formula will tell you how many of each element you have in the compound. But the empirical formula only tells you the ratio between those two elements, or 3 and 4, you name it. But there are only two elements over here. To make the nice, smallest possible integer ratio between carbon and hydrogen is to find out the biggest multiple, common multiple number, and divide those two numbers by that. Okay. So obviously 2 and 6, the common multiple will be 2. Perfect. Perfect. So if you do divide those two numbers by 2, you will have, instead of C2, it will be C1, okay, and H3, not 6. And that is your empirical formula of this molecular formula. So if I look at the empirical formula here, and you're saying, oh, this compound has 1 carbon and 3 hydrogen, that's wrong. Because this is actual numbers of each element and actual compound. That is only shown in molecular formula, but empirical formula will tell you the nice integer ratio between these two. That's the difference. Makes sense, right? This is what we discussed before too. And let's try to do the practical problem out of this one, okay? So keep this in your mind real quick. So there is a unknown molecular formula. Is an unknown molecular formula of compound. Okay? But only thing that you know about this compound is empirical formula. Okay. So that is C1H2O. Okay. But once again, you don't know about the molecular formula yet. But luckily, you know the empirical formula, and also, thankfully, you find out that the molecular weight of the compound was 180 grams. Okay. So in here, you actually going backward. So you know the empirical formula, and now you're trying to find out the empirical molecular formula if you have molecular weight of the compounds. Okay. So in this case, this is also quite easy, simple steps that you need to follow to get the actual molecular formula. When you get the empirical formula here, try to get the molecular weight. This is kind of weird to say molecular weight, but just the sum of the atomic mass in this empirical formula. So there will be carbon, 1 carbon, 12, 2, but hydrogen is 1, right? 1 times 2. And this is what? 16, right? So if you do 12 plus 2 plus 16 is 30. Right? You good? And then try to divide actual molecular weight by empirical formula weight. Okay? You good, right? And that gives you what number?
6.
Perfect. 6. Perfect. We're done here. So when you get the 6, just multiply that number in here, 1, 2, 1, right? So multiply those number by 6. Okay? Then it will become what? C6H12O6. So now you find its actual molecular formula. So we're actually doing backward. Okay? Makes sense, right? Good, perfect, great. So let's do one more. At this time, I'll give you a problem so you can try it. Okay. Okay. So let's say empirical formula of this one is CH2O. Still the same. Okay. Still the same. But molecular weight now is 90 gram per mole. Okay. What's the molecular formula of this one? Okay, I'll give you about 2 minutes. I think this is quite not very time-consuming calculation work is required. So maybe just 2 minutes. Yep, that is correct. So, once again, this will make the empirical formula weight will be what? Same, right? We did again 30, perfect. So if you divide by 30, you make 3, and just multiply those number by 3. Okay, so it'll be C3H6O8. We're done. Okay, makes sense, right? Okay, perfect. You want to do one more? One more? Okay, let's do one more. So how about empirical formula is just the CH2. Okay, just this CH2. Oh no, let's do it that way. Okay, CH2. Okay, and then empirical formula of this one is the 56. And then find out the molecular formula of this compound. Okay, so empirical formula is CH2, and molecular weight of that one is the 56. Okay, just 2 minutes again. Okay, 1 minute. Okay, so yeah, we'll do the same thing over here. We're gonna do the empirical formula weight, which is 12, and there's 2 hydrogens, so we plus 1 times 2. Okay? That makes 14, and then you divide this number molecular weight by 14. That is 4. Okay, so that makes what? 1. Perfect. C4H. So we just simply multiply those 2 numbers by 4, because we found 4 over here. Okay, I think it's good, right? No? Okay, perfect. All right, it's good. All right, so that's the other one we did was also about the percent composition. Like I mentioned before, this is all by mass. Oh, yeah, okay, let's do this first. I have another one to talk about, but yeah, so let's do this first. So if we want to do the percent composition by mass, it's pretty much simple. So this is your methane here, CH4. Okay, only thing you have to do is try to get the molecular weight of the whole compound, which is 12 plus 1 times 4. it makes 16 gram per mole. So you have a 16 gram per mole as actual molecular weight. And then if you want to do the percent composition for carbon in the methane, then you can try to get the atomic mass of carbon, okay, which you see on the periodic table given on the exam, so don't worry about it, but that's 12. And there is only one, right? So only one over this the molecular weight, which is 16 gram per mole. Okay, so that makes what? 1 times 12 is just 12 over 16. Okay, so that actually tells you for carbon, you have 70% of methane is carbon mass. So that means if you have 100 grams, if you have 100 grams of methane, the 75 grams of mass is coming from carbon, because it's the percent composition for carbon in this methane. Okay, makes sense, right? Okay. So if that is the case, maybe you can try this one too. Okay, maybe on the exam, I'll tell you this one. Okay, so maybe I can tell you 6. No, maybe let's make it this one over here, and try to find out the percent composition of hydrogen. Okay, so I'll give you about 3 minutes. Okay, so try to find out what's the percent composition of hydrogen by mass in this compound. How many grams of this whole compound will be determined by hydrogen? That's what it really means. Okay. So try to get the atomic mass of a hydrogen and multiply by the numbers of it, which is 8, over this whole molecular weight, and multiply by 100%. So you can get the numbers in percent unit. Okay, about 2 minutes. 1 minute. So the point is, I think the 50% or 30% of the exam problem will be requiring some calculation work. Like I don't know if you watched the video last time, there will be about 25 questions on the exam, meaning we have 50 minutes to do the exam, right? So if you can finish each question by 2 minutes, that means you're on the right pace. So if you have this type of a question, it takes even longer time, right? So if you get used to those type of calculation required problems, you have enough time for the exam date, okay, for the exam. So anyway, so okay, so this is also the same thing. We tried to get the 1. It's actually 1.008, but I'll just put 1, okay, over this is 12 times 3 plus 8. So this is like what, 44, right? 44, okay, and times, is it 44, right? Yeah. So then you multiply by 100%, okay. There will be what number? Could you guys do this for me? 8 over 44 times 100. So 18, right? Yeah. It should be less than 20. Yeah. So the 18 is. Okay. That's it. Makes sense, right? Okay. All right. All right. We're doing this. So probably we're gonna do more of a review, and then later we're gonna touch on the next chapter. But before the exam date, try to spend most of the time for just doing practical problems for the exam, so we can be 100% sure what we're gonna do. So the next one is actually coming from chapter 1. So if you guys remember this, you have a atomic model. So I'll give you two. The first one was the Bohr's model. And then the other one was the cloud one. Okay. So Bohr's model, you have a nucleus at the center. You have electrons moving on certain orbits. Later, we're gonna upgrade to the orbital, which is in 3D. But for now, for Bohr's model, you can have some orbits around the nucleus. This will make whole thing atom in the Bohr's model. Okay. Atom over here. The cloud is more like a realistic data. You're gonna have also a nucleus at the center, but you have a cloud instead of orbits, and it actually represents the density of the electron. Meaning, if you have go into close to the nucleus, you have a higher chance to find the electron nearby nucleus. Then those are the reasons we will have a very dark cloud. Okay, but obviously if you're being far away from your nucleus, you have a less and less chance to find the electron nearby, right? Because it's far away from there. So then you're gonna have kind of a fainter or lighter cloud on the outside, and that makes more realistic electron distribution around the nucleus in your model of the atom. Okay, so this is a very modern physics slide. This is the classic one. We still use this one for the some energy calculation. That's why we still learn about this model time to time in chemistry. Anyway, so if you have those type of things, you have a nucleus is made of what? Neutrons and protons, right? You guys remember this, right? Neutrons and protons there. And the electrons are moving around the nucleus once again. And then they're negatively charged. And this neutron is literally neutral. And this is a positive charge. Protons are positive charged. Okay. And then if you guys remember this one, right? Atomic number given to each different element in your periodic table is the same as numbers of protons. You guys remember this? Okay. And then if you see the atomic mass number, that is equal to numbers of protons and numbers of neutrons. Okay. So in here, atomic mass number, we don't count for the electron. So electron is about 100,000 times smaller in mass than the neutron and the proton. And neutron is very slightly 0.1% wise heavier than proton, but they're almost in the same mass. So anyway, so that's why we don't use the electron in here for atomic mass number here. So this is the numbers we can have for the elements, and then we write on the symbol. For example, if you have a carbon here, you have numbers on the top right corner of the periodic table there, which is, well, carbon is 6, right? So we use them on here, okay, 6. Because the atomic number 6 means it's carbon, okay? If it changes to 7, that's automatically become nitrogen. It's not carbon anymore, okay? So if you look at, anyway, so then this is atomic number that you put right on this side of your chemical symbol, chemical elements. And this is what you put on the top, left top corner of your elements. So it's 12. Okay. Makes sense, right? And this is where you put the numbers for formal charge. So formal charge is the given charge based on numbers of protons and electrons. Because the, like I said, proton is positively charged and electrons are negatively charged. So in this case, for formal charge-wise, you don't have to work with the neutral numbers of neutron. But if you don't see any numbers on here, means you can always assume there is a 0. Number 0 is implied there. You just don't see it there because you don't have to, and chemical rate. So that means it's 0 means it's neutral. It actually tells you, so this is atomic number, which is numbers of proton. And you know the atomic mass number as well. Then it doesn't say anything about here, but this carbon now at the moment has 6 electrons. because it's neutral. To this carbon to be neutral, there's 6 protons. It has to have 6 electrons there. It just implied there. So by just looking at this one, we know there will be 6 protons, 6 neutrons, and 6 electrons. Makes sense, right? But if you change this one to positive charge, now you have 1 positive charge means you have 1 less numbers of electron than the ones of proton. So that's why it becomes positive charged. Because it's missing 1 electron to be neutral form. Makes sense, right? So in this case, you have 6 protons, 6 neutrons, but 5 electrons. Okay? So on your exam, I'll give you this carbon over here, and I'll probably don't even show you 6 down here. Why? Because it's 6. To be carbon, it has to be 6. I mean, it's really, you don't need to put, but only thing you really need to put is this one. In case of you see the isotopes of what? Carbon. It could be 13 carbon, 14 carbon. It has the 6 protons still, but maybe 7 or 8 neutrons. That makes even heavier carbon, but still same chemical element because it's still 6 protons. So that would be carbon 13, carbon 14, which are much less abundant than your carbon 12. That's why you have an atomic mass number of carbon is very close to 12. Anyway, so if in this case I put negative charge here. Can you guys count the numbers of protons and neutrons and electrons? Oh, let's change this one to carbon 13. Okay, let's try to, yeah. Can you guys do this real quick? So you have a carbon 13 that has a negative charge on it as its formal charge. And I just wanted to count for numbers of protons and neutrons and electrons in this chemical compound, chemical atom right now. Makes sense, right? Because you have an atomic mass number there. You know for sure it has to be 6 proton, which is atomic number for the carbon, because it's a carbon. So you don't even put the 6 there. It's okay. This is, you know, it's a 6 to be carbon. But now it's a negative charge. So count the numbers of protons and neutrons and electrons by looking at the symbol right there. Okay, I think it's done, right? So how many protons still? 6. How about neutron? Will be 7. Perfect. It has to be 7 to make 13 to make this sum. But electron, you have more than what you said. Perfect. So you have more than 6 that makes this carbon 1 extra negative charge there. So it's negative 1. Okay. Makes sense, right? Good. So if I do anything on the formal charge with the isotope of the chemical element, this is how you can count the numbers of protons, and neutrons, electrons. They're all subatomic particles in your atom. Okay, makes sense, right? Yeah, perfect. So let's do couple more, and then we'll do the extra credit. So like you talked before, we have certain compounds looks like this. We did before in the glucose over here, right? And then when we use the molecular weight, you use the gram per mole, or use the atomic mass unit, AMU. That's okay, but this moles number, as you remember from a previous lecture, is actually meaning a Avogadro number. So this is a really big number we're talking about, which is 6.022 times the 23rd numbers. So if you have this many numbers of something, you can say, oh, I have 1 mole of that. That's what we can say in using Avogadro number. So if I say we have 0.5 moles, 0.5 moles of glucose right here. Okay, I just on your exam I said we have 0.5 moles of glucose, and tell me how many hydrogen in this glucose. In actual number. So meaning, what you all you need to do is this one. You know this is 0.5 moles, okay? Moles over here, and you try to multiply this one by Avogadro number. So if you have anything on the 1 mole, you know this many is the actual numbers of that, right? So in that case, you'll be find that, oh, this is the numbers of actual numbers of the glucose over here by just doing this one, okay? So if you do this one real quick, this will become half the, this one. Okay, you have this many of glucose, right? Okay, so if you do this one, and then only thing you have to know is each glucose has 12 hydrogens, right? So you have 3.0, this is 1 times 10 to 23rd glucose. But it has what? 8 hydrogens in each glucose, okay? Over glucose. Okay. So if we multiply this number by 8, right? Which will become 2.4088 times 10 to 24. Okay? Hydrogens will be there in total glucose number. Makes sense, right? Because this is the amount of the glucose we have, right? So it's 0.5 moles, but 1 mole is about Avogadro number, so it's only half of that. So we just have only this many moles, this many numbers of glucose. But each glucose has a 12 hydrogen in it, so actually just for hydrogen atomic numbers of hydrogen atoms are multiply that actual numbers of glucose by 8. So each one has 8. So that will give you a total numbers of hydrogen atom in the glucose. Okay, makes sense, right? Does it make sense? You good? Okay, let's try to do a practical problem with this one. Okay. All right, let's make it a bit more. Okay, so if you have a 2 moles methane, okay, how many hydrogen atoms are there? Yeah, can you guys try this one real quick? So you have a 2 moles of methane. And how many hydrogen atoms will be there in 2 moles of methane? And Avogadro number is once again 6.022 times 10 to 25. That's Avogadro. That's what 1 mole means. Okay, but you have 2 moles instead of 1 mole.
So did you double that?
Perfect. That's a very good start right there. Perfect. And then try to see how many hydrogens in 1 methane, and that's the almost done. Okay. Okay, so maybe just another minute and we'll do this together. Okay. And let's have some time for extra credit. So probably even on Friday, I'll focus on the mathematical problems first, and maybe next week we'll work on the conceptual and factual problems you may see on the exam. Okay? And then if you have some time still, then we can move on to next chapter. But still, exam 1 will cover chapter 1 and 2 and 3. So that's okay. All right. So the 2 modes, meaning what? You have 2 modes, right? So each mode has this many. So it'll be 1.2, 1.0 times 4 times 10 to 24, right? Okay. And then you have, but this is numbers of methane, but each methane has 4 hydrogen. So we're gonna multiply this number by 4. Hydrogen over methane, right? 4. So that would be 4.8, 156 times 10 to 24. So you have this many numbers of hydrogen. Okay? Makes sense, right? Good. So let's stop here. I'm probably going to do all the other mathematical problems on Friday, and let's move on to the other types of problems on next week. Okay. Let's stop here today.